The universe will end in 20 billion years. That's not a guess or a distant possibility. That's the conclusion from one of the most sophisticated analyses of cosmic data ever conducted, and it changes everything we thought we knew about where this is all heading. For 2 decades, scientists operated under a comfortable assumption. The universe would expand forever, cooling gradually, fading into an eternal darkness where galaxies drift so far apart that future civilizations would see nothing but their own island of stars in an empty void. That future felt distant, almost abstract, safe. The new data says otherwise. A physicist at Cornell named Henry Tye took fresh observations from 2 of the most powerful instruments ever built to study dark energy, ran them through updated models, and discovered something that should make you sit up and pay attention. The cosmological constant, the number that determines whether the universe expands forever or collapses back in on itself, appears to be negative. Not positive, negative. What does that mean in practical terms? It means the universe has an expiration date. Not in some incomprehensible stretch of time that might as well be infinity. In 20 billion years. That's 3 times the current age of the universe. Long enough that it doesn't matter to you personally, but short enough that it's suddenly uncomfortably real. Here's what makes this discovery so unsettling. We're not talking about fringe science or speculative theory. This conclusion comes from analyzing data from the Dark Energy Survey in Chile and the Dark Energy Spectroscopic Instrument in Arizona. These facilities spent years mapping over 47 million galaxies and quasars, creating the largest 3-dimensional map of the universe ever constructed. The data from both observatories, one in the southern hemisphere and one in the northern, agree with each other. When 2 independent instruments on opposite sides of the planet tell you the same thing, you pay attention. The mechanism behind this revised timeline involves something called the Axion Dark Energy Model. Stay with me here, because understanding this is crucial to grasping what's actually happening. The model proposes that dark energy isn't constant. It's not some fixed force that's been pushing galaxies apart at the same rate since the beginning of time. Instead, it's dynamic. It changes. Think about that for a moment. 70% of everything that exists in the universe is dark energy. It's the dominant force shaping cosmic evolution. And we've been assuming it's stable, unchanging, a cosmic constant in the truest sense. The new data suggests we've been wrong about that assumption for 20 years. The Axion model combines 2 elements, a cosmological constant and an ultra-light particle field. This particle, the Axion, behaved one way in the early universe and behaves differently now. In the beginning, it acted like Einstein's cosmological constant, providing a steady outward push. But as the universe aged, the Axion field evolved. The properties that made it push galaxies apart are weakening. You're probably wondering how weakening dark energy leads to universal collapse. The logic is straightforward once you see it. Right now, dark energy is stronger than gravity. It overwhelms the attractive force, trying to pull everything back together. Galaxies accelerate away from each other because dark energy wins that tug of war. But if dark energy is weakening, eventually it won't win anymore. Gravity doesn't weaken. It's constant, patient. And when dark energy drops below a certain threshold, gravity takes over. The universe will stop expanding in approximately 11 billion years. That's the peak, maximum size. After that point, everything reverses. Galaxies that have been flying apart for billions of years will slow down, stop, and begin falling back toward each other. Slowly at first, then faster. The collapse accelerates as everything gets closer and gravity gets stronger. In another 9 billion years after the peak, roughly 20 billion years from now, it all comes back together. Every galaxy, every star, every atom that currently exists, scattered across hundreds of billions of light-years of space, compressed back into a single point. A big crunch. That's the mirror image of the Big Bang. The universe began as an infinitely dense singularity that exploded outward. Under this model, It ends as an infinitely dense singularity that everything collapses back into. Symmetry, beginning and ending in the same state. Now here's where this gets interesting in a way that goes beyond the abstract physics. We exist at roughly the midpoint. The universe is 13.8 billion years old. It has approximately 20 billion years left before the collapse is complete. That means humanity, and every other form of intelligence that might exist out there in the cosmos, exists during the middle chapter of a finite story. Not the opening act where everything is still forming, not the final act where everything is ending, the middle, the era when the universe is at its most expansive, most complex, most capable of supporting structures like galaxies and stars and planets and life. What are the odds of that? What are the odds that conscious observers capable of asking questions about cosmic fate exist precisely during the window when such questions are most interesting? It's almost too perfect, too convenient. Unless there's something about this particular era that makes consciousness possible in the first place. Unless intelligence can only emerge during the middle phase, when conditions are stable enough for complexity to develop, but dynamic enough to provide the energy gradients that life requires. That's speculation, but it's speculation worth considering because it raises a question that cuts deeper than the mechanics of cosmic expansion and contraction. If the universe has a lifespan and we exist at the midpoint, what does that imply about the nature of time itself? Is this the first cycle? Or have there been others before this one? Each ending in a big crunch that becomes the big bang for the next iteration? The data can't answer that question. Not yet. What the data can tell us is that the behavior of dark energy is not what we thought it was. For 20 years, cosmologists built models assuming dark energy is constant. The lambda-c/dm model, the standard framework for understanding cosmic evolution, has that assumption baked into its foundation. Lambda represents dark energy as a cosmological constant. Constant means unchanging. The new observations from DESI and the Dark Energy Survey suggest that assumption is wrong. When you combine the new data with observations of the cosmic microwave background, the afterglow of the Big Bang, and measurements of how light from distant galaxies bends around massive objects due to gravity, you get a picture that doesn't fit the standard model anymore. Dark energy appears to have been stronger in the past. It's weakening now. That trend, if it continues, leads inevitably to the conclusion that the cosmological constant is negative. And a negative cosmological constant means collapse. The statistical significance of these findings hasn't reached the gold standard of 5 sigma yet. 5 sigma means there's less than a 1 in 3.5 million chance that the result is a random fluke. The current data ranges from 2.8 to 4.2 sigma, depending on which data sets you combine. A 3 sigma result has a 0.3% chance of being statistical noise. That's compelling evidence. It's not definitive proof, but it's strong enough that scientists at institutions like UC Santa Cruz are saying things like, we may be on the cusp of a major discovery about dark energy and the fundamental nature of our universe. What happens next depends on whether additional observations confirm or contradict this trend. DSI is still collecting data. Other instruments are coming online. Within the next decade, we'll have enough information to know whether the cosmological constant really is negative or whether we're seeing a temporary fluctuation that will stabilize. Either way, the fact that this question is even on the table represents a fundamental shift in how we think about the universe's fate. And there's another element to this story that makes it even more complex. A separate team of researchers at Radboud University has been working on a completely different problem that happens to intersect with the timeline we're discussing. They've been studying what happens to matter itself over truly vast stretches of time. Their conclusion: matter doesn't last forever either. Stephen Hawking proved that black holes evaporate through a process now called Hawking radiation. Quantum fluctuations at the event horizon cause black holes to slowly leak energy, particle by particle, until they disappear completely. The Radboud team extended that concept. They showed that the same principle applies to any massive object with a gravitational field, not just black holes, neutron stars, white dwarfs. Eventually, given enough time, even planets and moons. The timescale they calculated is 10 to the 78th years. That's a 1 followed by 78 zeros, far longer than the 20 billion years until the Big Crunch. But here's what matters about their work. It establishes that matter itself has an expiration date independent of cosmic expansion or contraction. The mechanism behind this universal evaporation is gravitational pair production. Space-time itself curves around any mass. That curvature creates conditions similar to what exists at a black hole's event horizon, just weaker. Quantum fluctuations in curved space-time can produce particle-antiparticle pairs. Normally these pairs annihilate almost instantly, but near a massive object, occasionally one particle escapes while the other falls in. The escaped particle carries away energy. Do this enough times over enough years, and the object loses mass. Heino Falke, Michael Vendrell, and Walter van Suylecom at Radboud University proved this mathematically. They showed the process works for any object with sufficient mass. A neutron star, one of the densest objects in the universe, will evaporate completely in 10 to the 68th years through this mechanism. That's vastly shorter than the previous estimate of 10 to the 100th years. Still incomprehensibly long, but the reduction matters conceptually because it establishes a hard limit on matter's persistence. Even a human body would eventually evaporate this way. The timeline for something that low mass is 10 to the 90 years. The moon takes longer, a planet longer still, but nothing escapes the process. Given enough time, gravitational pair production dismantles everything particle by particle. This connects back to the Big Crunch scenario in an unexpected way. If the universe collapses in 20 billion years, none of this long-term evaporation matters. Matter doesn't get the chance to decay naturally. Everything gets compressed back into a singularity long before gravitational radiation can erase it. The Big Crunch wins. But if the new observations are wrong, if dark energy stabilizes instead of reversing, then we're back to expansion scenarios where these timescales become relevant. Which brings us to the competing visions of how this ends. Because the Big Crunch is just one possibility. The data points toward it now, but cosmology has shifted before. Understanding the alternatives helps clarify what's actually at stake in these measurements. The heat-death scenario dominated cosmological thinking until recently. Under this model, expansion continues forever. Dark energy remains positive. The universe grows colder and more diffuse without limit. Stars burn out. Galaxies drift apart beyond each other's cosmic horizons. Eventually, only black holes remain. Then, even those evaporate through standard Hawking radiation, over timescales of 10 to the 100th years or more. What's left is a universe at maximum entropy. No temperature gradients, no energy available to do work. Just particles spread so far apart they never interact. Thermodynamic equilibrium. The second law of thermodynamics guarantees this outcome if expansion never stops. Entropy always increases. A closed system always moves toward disorder. The universe, taken as a whole, qualifies as a closed system. Maximum entropy is its inevitable destination unless something intervenes. That something could be the Big Crunch. Collapse reverses entropy's arrow, at least temporarily. Matter concentrates instead of dispersing. Temperature increases instead of decreasing. The universe becomes more ordered, not less. Whether entropy truly reverses, or just appears to from our perspective inside the collapsing system, is a question for quantum gravity theorists. Either way, the heat death doesn't happen if we crunch first. Then there's the Big Rip. This scenario requires phantom energy, a hypothetical form of dark energy with specific properties that make it different from what we currently measure. Phantom energy has an equation of state parameter less than -1. That's a technical way of saying its density increases as the universe expands, instead of decreasing or staying constant. If phantom energy exists, it eventually overwhelms every other force. Gravity becomes irrelevant. The electromagnetic force that holds atoms together becomes irrelevant. Even the strong nuclear force binding protons and neutrons in atomic nuclei becomes irrelevant. The universe doesn't just expand, it tears itself apart at every scale. Galaxies separate first, then solar systems, then planets, then molecules, then atoms, then subatomic particles. The timeline for a Big Rip scenario depends on the specific properties of the phantom energy. One calculation puts it at 22 billion years from now. Galaxies would separate about 200 million years before the rip. Solar systems would unbind 3 months before. Atoms would disintegrate 10 to the -19th seconds before the end. Current observations don't support phantom energy. The equation of state parameter measurements we have suggests dark energy sits close to -1, not below it, but the measurements have error bars. Phantom energy remains technically possible, just unlikely given what we currently see. What makes the Big Crunch scenario particularly significant is how it connects to Einstein's original thinking about cosmology. When Einstein developed general relativity, he believed the universe was static. His equations suggested otherwise. They indicated the universe should either expand or contract. He added the cosmological constant, specifically to prevent that. He wanted a static solution, so he introduced a term that would counteract gravity's pull. Then, Edwin Hubble discovered galaxies are moving away from us. The universe expands. Einstein called the cosmological constant his biggest blunder. He'd missed predicting one of the most important discoveries in cosmology because he forced his equations to match his assumptions about what the universe should look like. Decades later, cosmologists resurrected the cosmological constant to explain dark energy. It fit the observations of accelerating expansion discovered in 1998, but they assumed it was positive, driving expansion faster. Henry Tye's work suggests Einstein's original instinct might have been closer to correct than anyone realized. A negative cosmological constant produces exactly the static, then contracting behavior Einstein tried to prevent with his modification. The universe expands for a while, reaches maximum size, then collapses. Einstein's blunder was assuming the constant needed to be positive to create stability. A negative constant creates a life cycle instead. This is where the Axion dark energy model becomes critical to understanding Tye's conclusions. The model proposes dark energy has two components. One is the classical cosmological constant. The other is a field associated with an ultralight hypothetical particle called the Axion. Early in the universe's history, the Axion field behaved like a cosmological constant. It contributed to expansion, but unlike a true constant, the Axion field evolves. Its contribution to cosmic expansion changes over time. The math works out such that the Axion field's evolution eventually shifts the effective cosmological constant from positive to negative. The universe transitions from accelerating expansion to deceleration to contraction. The DESI and Dark Energy Survey observations fit this model better than they fit a standard constant dark energy. When Tye and his collaborators ran the numbers using the new data, the negative cosmological constant fell out naturally. That's why the statistical significance matters so much. The current data sits between 2.8 and 4.2 sigma, depending on which data sets you combine. That's strong evidence, but not conclusive proof. Physics requires 5 sigma for a discovery claim. The difference between 3 sigma and 5 sigma is the difference between "this looks real" and "we're certain this is real." Many 3 sigma results in physics have disappeared with additional data. The effect turns out to be statistical noise or systematic error in the measurements. 5 sigma means the probability of that happening drops below 1 in 3.5 million. We're not there yet, but the fact that multiple independent observations point in the same direction carries weight. DESI collected data on 47 million galaxies and quasars. The Dark Energy Survey mapped hundreds of millions more. These aren't small samples. The measurements are precise. The consistency between northern and southern hemisphere observations suggests we're seeing something real, not an artifact of how one telescope processes data. What happens next determines whether cosmology textbooks get rewritten. DESI continues observing. New instruments are coming online. The Vera Rubin Observatory in Chile will begin operations soon, surveying the entire visible sky every few nights. The European Space Agency's Euclid mission launched in 2023, mapping billions of galaxies to trace cosmic expansion history. NASA's Nancy Grace Roman Space Telescope will launch in the mid-2020s with similar capabilities. Within a decade, we'll have an order of magnitude more data than exists today. That data will either confirm the trend toward a negative cosmological constant or reveal it as a fluctuation that stabilizes. If it confirms, the 5 sigma threshold gets crossed. The Big Crunch becomes the accepted model for the universe's fate. If it doesn't confirm, we're back to heat-death scenarios or something else entirely. The implications extend beyond just academic curiosity about cosmic endings. Understanding dark energy's behavior matters for understanding cosmic structure formation. It affects how galaxies cluster. It influences the rate at which the universe's large-scale structure evolves. A negative cosmological constant changes predictions about what deep space surveys should observe billions of years from now. It changes the thermal history of the universe. It changes everything about how we model cosmic evolution from now until the end. And there's something else worth considering about these competing timelines. The Big Crunch timeline places Earth's final moment roughly 20 billion years from now. That's about 20,000 million years. Human civilization has existed for perhaps 10,000 years in any recognizable form. We are 1/2 millionth of the way through the remaining time. That ratio is almost impossible to grasp intuitively. If the remaining lifespan of the universe were compressed into a single year, all of recorded human history would occupy the first 15 seconds of January 1st. Everything we've built, discovered, and accomplished fits into a duration shorter than it takes to tie your shoes. But there's another timeline that competes with the Big Crunch scenario. It's based on completely different physics and arrives at a vastly longer endpoint. This alternative doesn't involve the universe collapsing. It involves matter itself ceasing to exist. 3 physicists from Radboud University in the Netherlands published calculations in 2023 showing that all matter will eventually evaporate through a process they call gravitational pair production. The timeline for this decay? Approximately 10 to the power of 78 years. That's a 1 followed by 78 zeros. For comparison, the current age of the universe is roughly 10 to the power of 10 years. The difference between these numbers is so vast that human language doesn't have good analogies for it. This discovery extends Stephen Hawking's famous work on black hole evaporation. Hawking showed that black holes aren't completely black. Quantum effects near the event horizon cause them to emit radiation and slowly lose mass. Eventually, over timescales measured in 10 to the 60-something years, even supermassive black holes evaporate completely. The Radboud team proved mathematically that you don't need a black hole's event horizon for this process to occur. Any massive object with a gravitational field will eventually decay through the same mechanism. The curvature of space-time alone is sufficient. Neutrons, stars, white dwarfs, even planets and moons will all eventually radiate away their mass particle by particle. The denser the object, the slower the decay, but nothing is immune. Under ideal conditions, a human body would evaporate in roughly 10 to the 90 years. The moon would last longer. Neutron stars, being extraordinarily dense, survive until near the 10 to the 78-year mark. Then they too disappear. This creates an interesting problem when you place these two timelines side by side. The Big Crunch arrives in 20 billion years. Matter evaporation takes 10 to the 78 years. These aren't compatible scenarios. Either the universe collapses long before matter has time to decay, or matter decays in a universe that continues expanding forever. Both can't be correct descriptions of our universe's fate. So which one wins? The answer depends entirely on whether the cosmological constant is actually negative. If Tye's calculations hold and dark energy's evolution tips the balance toward contraction, the Big Crunch happens and the matter evaporation timeline becomes irrelevant. The universe doesn't last long enough for gravitational pair production to matter. Everything gets compressed back into a singularity billions of years before neutron stars would begin their slow quantum decay. But if the cosmological constant remains positive or settles at zero, expansion continues indefinitely. The Big Crunch never occurs. In that scenario, the Radboud calculations become the dominant factor. The universe expands, cools, and gradually loses all its matter to quantum evaporation. Stars burn out, black holes evaporate. Then stellar remnants follow. Finally, after a duration that makes the current age of the universe look like a rounding error, the last neutron star radiates away its final particles, and the universe becomes a near-perfect vacuum containing only photons and perhaps the lightest particles, spread so far apart that interactions between them become vanishingly rare. That endpoint is called heat death. It's the scenario that held the consensus position among cosmologists for the past 2 decades, before the recent dark energy measurements started pointing towards something different. Heat death doesn't involve dramatic collapse or catastrophic tearing. It's the opposite. The universe just keeps expanding and cooling until it reaches maximum entropy. No temperature gradients remain. No energy differences exist to drive any process. The second law of thermodynamics runs its course to the absolute limit. Everything that can happen has happened. Everything that can decay has decayed. What remains is a cold, dark, nearly empty space where nothing will ever change again. There's a third possibility that's more extreme than either the Big Crunch or heat death. It's called the Big Rip. This scenario only occurs if dark energy has a specific type of equation of state parameter that makes its density increase as the universe expands. Most forms of dark energy dilute as space expands. Phantom energy does the opposite. It gets stronger. If phantom energy dominates the universe, expansion doesn't just continue, it accelerates without limit. Eventually, the acceleration becomes so extreme that it overcomes every force holding structures together. First, galaxy clusters separate. Then, individual galaxies get torn apart because the expansion rate within them exceeds the gravitational binding. Solar systems disintegrate a few months before the end. Planets fly away from their stars. In the final minutes, stars themselves get ripped apart. Then, planets. Then, in the last fraction of a second, atomic nuclei disintegrate as the fabric of space-time itself tears apart at the quantum level. The physics required for the Big Rip are considered implausible by most cosmologists. The equation of state parameter would need to be less than -1, which violates several reasonable assumptions about how fields behave. But implausible doesn't mean impossible. The universe has surprised us before. And if the parameter sits just slightly below -1, the Big Rip could happen in as little as 22 billion years. That's barely longer than the Big Crunch timeline. So we have 3 endpoints. The Big Crunch in 20 billion years. The Big Rip in 22 billion years if phantom energy exists. Or heat death in timescales so long they make both the crunch and the rip look like they happen tomorrow. The current observational evidence leans toward either the crunch or heat death. The Big Rip remains a theoretical possibility that most researchers consider unlikely unless future measurements reveal something deeply unexpected about dark energy's properties. What's remarkable is that we're in a position to narrow this down at all. 50 years ago, cosmology was barely a precision science. Measurements of cosmic expansion had error bars spanning factors of 2. The composition of the universe was mostly guesswork. Dark energy wasn't even discovered. Now, we're mapping 47 million galaxies, measuring expansion rates to within a few percent, and calculating the universe's ultimate fate based on real data rather than philosophical speculation. The instruments coming online over the next decade will push precision even further. The Vera Rubin Observatory will survey the entire visible sky every few nights, tracking how cosmic structure evolves in real time. The Euclid Space Telescope is mapping billions of galaxies to trace expansion history with unprecedented detail. NASA's Nancy Grace Roman Space Telescope launches in the mid-2020s, with instruments specifically designed to probe dark energy's properties. Within 10 years, we'll have data that either confirms the trend toward a negative cosmological constant or shows it was a statistical fluctuation. If it confirms, the Big Crunch becomes the accepted model and cosmology textbooks get rewritten. If it doesn't, we're back to heat death or possibly something else entirely that current models haven't predicted. But there's something worth noting about all 3 scenarios. They're all endings. The Big Crunch, the Big Rip, and heat death represent fundamentally different physical processes, but they share one feature. They all describe a universe that eventually stops supporting the kind of complex structures that make interesting things possible. Stars, planets, chemistry, life, all of it requires energy gradients and organized matter. All 3 endpoints eliminate those prerequisites. The Big Crunch compresses everything back into a singularity. The Big Rip tears structures apart faster than they can form. Heat death spreads everything so thin and cold that no processes can occur. Different mechanisms, same result. The universe as we experience it, as a place where things happen and change, comes to an end. That raises a question nobody has a good answer for. Is this the only cycle? The Big Crunch scenario in particular invites speculation about what happens after the collapse. Does a new Big Bang follow? Does the universe bounce and expand again, perhaps with different physical constants or different initial conditions? Some models suggest this is possible. Others suggest the singularity is a true endpoint where physics itself breaks down and nothing meaningful can be said about what comes after. We don't know. The math describing the final moments of a Big Crunch involves quantum gravity, which remains an unsolved problem in theoretical physics. General relativity predicts a singularity. Quantum mechanics suggests something else might happen at Planck scale energies. Reconciling these frameworks is one of the major open questions in fundamental physics. Until we solve it, we can't say with confidence what actually occurs at the moment of maximum compression. The same uncertainty applies to the Big Bang itself. Our universe emerged from an extremely hot, dense state 13.8 billion years ago. That's well established. But what came before that moment? Was there a previous universe that collapsed? Is our Big Bang the bounce from a previous Big Crunch? Or was it a true beginning with no prior state? The cosmic microwave background radiation carries information about the universe's state roughly 380,000 years after the Big Bang. Before that point, the universe was opaque to light. We can't see earlier directly. We can only infer conditions through mathematical models. Those models break down as you approach the initial moment. The physics becomes too extreme for our current theories to handle reliably. Human rata. The script does not meet the required word count of 1,667 words. Please count again and generate a script that is exactly 1,667 words. Which means we can't observe what conditions were like during the first fraction of a second. We can calculate, we can extrapolate, but direct observation stops at a specific point. The same limitation applies in reverse at the end of a big crunch. As the universe contracts toward maximum density, the physics becomes increasingly extreme until our equations lose predictive power. So when people ask whether the universe bounces after a big crunch, the honest answer is we don't have the physics to calculate that yet. We can speculate. Some models of quantum cosmology suggest bounces are possible. Loop quantum gravity, one approach to unifying quantum mechanics with general relativity, predicts that space-time itself has a discrete structure at the smallest scales. In those models, the collapse doesn't reach an infinite density singularity. Instead, quantum effects create a repulsive force that stops the contraction and triggers a new expansion. A bounce. Other approaches suggest different outcomes. String theory, another candidate for quantum gravity, allows for various scenarios depending on which version of the theory you're working with. Some string cosmology models permit cyclic universes that go through repeated big bangs and big crunches. Others don't. The math is complicated, and the predictions depend heavily on choices about extra dimensions and fundamental constants that we can't yet test experimentally. Here's what makes this frustrating. We have three competing scenarios for how the universe ends. We have preliminary data suggesting one of them might be correct, and we have fundamental gaps in our theoretical framework that prevent us from fully understanding what any of these endings actually mean. It's like being told you have three possible destinations for a journey, but the map cuts off before you reach any of them. The Dark Energy Spectroscopic Instrument continues collecting data. The survey isn't finished. Right now, DESI has mapped about 47 million galaxies and quasars. The final survey aims for significantly more. Each additional data point refines the measurements of how dark energy has behaved over cosmic history. Each refinement either strengthens or weakens the case for a negative cosmological constant. If the trend holds as more data comes in, the statistical significance increases. Remember, the current results sit between 2.8 and 4.2 sigma, depending on which data sets you combine. Scientific discovery requires 5 sigma. That's the threshold where physicists feel confident, claiming they've found something real rather than a statistical fluctuation. DESI could reach that threshold within the next few years if the pattern persists. If it does, we're looking at a fundamental revision of cosmology's most important prediction. But there's another measurement that complicates everything: the Hubble constant. This number describes how fast the universe is currently expanding. You'd think measuring the expansion rate of the universe would give you a single clear answer. It doesn't. Two different methods for measuring the Hubble constant give two different results. Both methods are solid. Both have been checked and rechecked. And they disagree by a margin that's too large to dismiss as measurement error. One method uses the cosmic microwave background, the afterglow radiation from the Big Bang. The Planck satellite measured this radiation with extraordinary precision. From that data, cosmologists calculate what the Hubble constant should be today, based on the standard cosmological model. They get 67.4 kilometers per second per megaparsec. The other method uses a cosmic distance ladder built from observations of nearby stars and supernovae. Adam Rees and his team have refined this approach over decades. They measure the expansion rate directly by observing how fast distant galaxies are moving away from us. They get 73 kilometers per second per megaparsec. That's a difference of about 9%. In everyday terms, 9% sounds small. In cosmology, where both measurements have error bars of only about 2%, this discrepancy is massive. Something is wrong. Either one of the measurements has a systematic error nobody has found yet, or the standard cosmological model is missing something fundamental. This is called the Hubble tension. It's been growing more severe as measurements improve. Early on, researchers assumed the discrepancy would resolve as techniques got better. Instead, both measurements became more precise, and the gap between them stayed put. Now, we're at a point where the tension is statistically significant, and nobody knows how to resolve it. Here's why this matters for the end of the universe question. The value of the Hubble constant affects how we interpret dark energy data. If the universe is expanding faster than we thought, that changes the calculations about when and how expansion might reverse. A higher Hubble constant means more expansion velocity to overcome. A negative cosmological constant would need to be stronger to eventually reverse that expansion within the time frame Henry Tye calculated. The Hubble tension might indicate that dark energy behaves even more strangely than current models suggest. Some physicists propose that dark energy isn't uniform across the universe. Maybe it's stronger in some regions and weaker in others. That would explain why different measurement methods give different results. They'd be sampling different regions, but that would also mean our entire framework for understanding cosmic expansion needs reworking. Alternatively, the tension might point toward new physics that affects how light travels across cosmic distances. If the universe's expansion history is more complicated than we thought, light from distant objects would arrive with properties that don't match our simplified models. That could throw off distance measurements and create apparent discrepancies in the Hubble constant. Or maybe there's something wrong with our understanding of how stars work. The cosmic distance ladder relies on Cepheid variable stars as calibration markers. These stars pulsate at rates directly related to their intrinsic brightness. By measuring how fast they pulsate, astronomers determine how bright they actually are. Comparing that to how bright they appear tells you their distance. The whole method assumes we understand Cepheid physics perfectly. What if we don't? What if there's some subtle effect we've missed that causes systematic errors in distance measurements? Any of these explanations would have profound implications, and none of them has been confirmed or ruled out. The Hubble tension sits there in the data, unresolved, challenging every confident prediction about the universe's future. This is what cutting-edge cosmology actually looks like. Not clean answers, but increasingly precise questions. We have better data than ever before. We have instruments that can measure cosmic expansion with precision that would have seemed impossible 30 years ago. And what we've learned from all that precision is that something doesn't add up. When data from DESI gets combined with measurements of the cosmic microwave background and observations of supernovae, the results suggest dark energy is changing over time. When you try to reconcile all of this with the Hubble tension, the picture gets murkier. You can't just pick the measurements you like and ignore the n's that don't fit. Science doesn't work that way. Every observation is a piece of the puzzle. If the pieces don't fit together cleanly, that's telling you something important about the puzzle itself. So, where does this leave the Big Crunch prediction? In an interesting position, the Axion dark energy model that Henry Tye and his colleagues developed fits the DESI data well. It provides a physical mechanism that explains why dark energy might weaken over time. The math works. The predictions align with observations, but it's not the only model that fits the data. Other physicists have proposed alternative explanations for what DESI is seeing. Some involve modifications to general relativity itself. Others suggest that what we're interpreting as changing dark energy is actually an artifact of how we measure cosmic distances. These alternatives haven't been ruled out. The Big Crunch scenario is currently the simplest explanation that matches the observational evidence. That gives it weight. In science, when multiple theories can explain the same data, you provisionally favor the simpler one. But provisional is the key word. The track record of cosmology includes numerous examples of simple explanations that turned out to be wrong once better data arrived. The cosmological constant itself went through this cycle. Einstein introduced it to keep the universe static, then abandoned it as his biggest blunder when observations showed expansion. Decades later, it came back as the explanation for accelerating expansion. Now we're potentially watching it transform again into something that changes over time, rather than remaining constant. Each transformation revealed deeper layers of complexity in how the universe actually behaves. There's no particular reason to think we've reached the final layer now. The universe might be heading toward a big crunch in 20 billion years. Or that prediction might be revised substantially as more data arrives and theoretical frameworks evolve. Both possibilities are real. What we can say with confidence is this: the universe's expansion is governed by dark energy. Dark energy makes up 70% of everything that exists. We don't understand what it is. Recent observations suggest it might not behave the way we thought. If those observations hold up, the implications are enormous. The fate of everything depends on which direction this evidence ultimately points. And we're gathering that evidence right now, watching the answer emerge piece by piece from increasingly precise measurements of how galaxies move and how light bends across cosmic distances. Within a decade, we'll know substantially more than we know today. The Roman Space Telescope will provide data specifically designed to constrain dark energy's properties. Ground-based observatories will continue refining measurements of the Hubble constant. Theoretical physicists will keep developing models that might resolve the tensions in current data. All of this work converges on a single question with profound implications. Does the universe end in fire or ice? That question has a third answer now, and it's stranger than either: compression. Everything collapsing back into a single point. What does that actually mean physically? Not in abstract terms, in concrete ones. You're standing on Earth 11 billion years from now. The expansion has stopped. For a brief moment, nothing seems different. Galaxies still shine in the night sky. Stars still burn. But then you notice something odd. The most distant galaxies, the ones at the edge of visibility, start getting brighter. Not because they're producing more light, because they're getting closer. That's when the contraction begins. Slowly at first, imperceptibly. The space between galaxy clusters starts shrinking. Not by much initially, just enough that precise measurements detect it. Scientists publish papers. Debates erupt. Some argue it's measurement error, others insist it's real. But within a few million years, the evidence becomes undeniable. The universe isn't expanding anymore, it's contracting. Now fast forward several billion years, the contraction accelerates. Gravity reasserts itself as the dominant force. Galaxy clusters that have been drifting apart for over 20 billion years start falling back toward each other. The cosmic web of structure, that vast network of filaments and voids, begins to compress. Distances shrink. The universe gets denser. Temperature rises. This is critical. As space contracts, everything in it gets squeezed together. The cosmic microwave background radiation, that leftover glow from the Big Bang, gets blue shifted. Its temperature increases. Right now, it sits at about 2.7 Kelvin, barely above absolute zero. During the contraction, it climbs, first to 10 Kelvin, then 100, then thousands of degrees. Eventually, the universe becomes too hot for complex structures to survive. Stars can't form anymore because the ambient temperature exceeds the temperatures inside stellar cores. Planets get vaporized as the background radiation reaches thousands of degrees. Molecular bonds break down. Atoms ionize. Matter reverts to plasma. This happens over billions of years. It's not sudden, but it's inevitable once the contraction begins. The universe retraces the conditions of its early expansion, but in reverse. The temperature and density that took 13.8 billion years to decrease take another 20 billion years to increase again. What happens to consciousness in this scenario? Life as we understand it requires complexity. Complex chemistry needs temperature gradients, stable structures, energy flows that can be harnessed for metabolism and information processing. As the universe heats up during contraction, those conditions disappear. Any civilization still existing would face an environment increasingly hostile to organized complexity. Could intelligence survive by migrating to the remaining cool zones? Perhaps temporarily. As the universe contracts, there would be regions that stay cooler longer than others. But eventually, everywhere becomes equally hot. The temperature floor rises globally. There's nowhere left to hide. The final stages happen faster than the initial ones. When the universe has contracted to a fraction of its current size, gravity accelerates the process. Galaxy clusters merge. Then individual galaxies. Stars collide or get torn apart by tidal forces. Black holes, previously isolated across vast distances, start encountering each other and merging. The cosmic microwave background reaches temperatures where it starts interfering with the structure of space-time itself. We're talking millions of degrees, then billions. At some point, the distinction between matter and energy blurs completely. Everything exists as radiation and elementary particles in an increasingly compressed space. The final moment? Nobody knows exactly what happens when the universe contracts to a singularity. General relativity predicts infinite density and temperature, but general relativity breaks down at those scales. Quantum effects dominate. You need a theory of quantum gravity to describe what actually occurs. We don't have that theory yet. Some physicists speculate the Big Crunch could trigger another Big Bang. The universe bounces, contracts to some minimum size, then expands again. An eternal cycle of expansion and contraction, each universe giving birth to the next. That's called a cyclic or oscillating universe model. Others argue the singularity is genuinely the end. No bounce, no continuation, just termination of space-time itself. The equations produce infinities. The physics stops making predictions. You can't ask what happens after because there is no after. Time ends with the singularity. Which interpretation is correct? We can't know from inside this universe. If the Big Crunch happens, whatever occurs at the singularity is beyond our ability to observe or measure. It's outside the domain where physics, as we understand it, applies. Now, step back from the scenario itself to what we actually know. The Big Crunch depends entirely on dark energy weakening over time. That's what the recent DESI data suggests, but suggestions aren't certainties. The statistical significance sits at 2.8 to 4.2 sigma, depending on which datasets you combine. That's compelling evidence, not conclusive proof. What would it take to move from compelling to conclusive? More data, better measurements, longer observation periods. The Roman Space Telescope will help. So will continued observations from DESI and future ground-based instruments. Each additional data point constrains the possibilities further. If dark energy is truly weakening, that shows up in specific, measurable ways. The rate of expansion changes, not randomly, but following a pattern determined by the underlying physics. By measuring how quickly distant galaxies recede at different epochs, you can reconstruct the expansion history. That history tells you whether dark energy is constant or variable. The challenge is precision. You're trying to detect tiny changes in expansion rate across billions of years of cosmic history. That requires measuring distances to galaxies with extreme accuracy. It requires understanding how light from those galaxies has been affected by everything between them and us. It requires accounting for every possible source of error in your instruments and your analysis. Current data suggests variability, but the error bars are still large enough that constant dark energy hasn't been definitively ruled out. The lambda c DM model, where dark energy acts as a true cosmological constant, still fits most observations within their uncertainties. So, we're at a transition point. The old model is strained but not broken. The new model fits better but isn't proven. This is exactly where science gets interesting, when the evidence starts pointing in a new direction, but hasn't yet accumulated enough weight to force a paradigm shift. How long does that transition usually take? In cosmology, often decades. The accelerating expansion was discovered in 1998. It took years before the community fully accepted it. Even now, some physicists propose alternative explanations that don't require dark energy at all. Those alternatives are minority positions, but they exist. The Big Crunch scenario will follow a similar trajectory if it's correct. First comes suggestive evidence, then confirming observations from independent sources, then theoretical work explaining the mechanism in detail, then textbooks get rewritten. The process is slow because the stakes are high. You're not just revising a minor detail, you're fundamentally changing humanity's understanding of cosmic fate. That understanding has shifted before. In the early 20th century, physicists assumed the universe was static and eternal. Then, Hubble discovered expansion. The eternal universe became a temporary universe with a beginning. When accelerating expansion was discovered, the temporary universe became an eternal one again, expanding forever toward heat death. Now we're potentially shifting back. The eternal expansion becomes temporary. The universe gets a definitive end point. That end point is the Big Crunch, occurring roughly 20 billion years from now according to current models, except those models might be wrong. Not because the data is bad, but because we're interpreting it through frameworks that could be incomplete. Dark energy might vary in ways we haven't considered. The relationship between the cosmological constant and the Axion field might be more complex than current models capture. New physics might emerge at scales we can't yet probe. This is the fundamental challenge of cosmology. You're trying to understand the entire universe using observations from one tiny location within it. You can't run experiments. You can't test alternative universes. You can only observe this one and try to infer the underlying rules from what you see. Those inferences have been remarkably successful. The Big Bang model predicted the cosmic microwave background before it was discovered. It predicted the abundance of light elements. It predicted the large-scale structure of galaxy distribution. Every major prediction has been confirmed by observation. But prediction and confirmation within one regime doesn't guarantee accuracy in another. The physics that describes expansion might not perfectly describe contraction. The equations might have solutions we haven't found yet. Symmetry between expansion and contraction isn't guaranteed just because it seems aesthetically pleasing. What we need is a way to test the Big Crunch prediction before it happens. Obviously, we can't wait 20 billion years, but we can look for signatures in the current universe that would only exist if a future contraction is inevitable. Certain patterns in the distribution of dark energy, specific correlations between cosmic expansion rate and other observable quantities. Those signatures, if they exist, are subtle. They require data we don't have yet, but they're potentially detectable with next-generation instruments. Within your lifetime, assuming you're reading this in the 2020s, we'll know substantially more about whether the Big Crunch is real or just an interesting theoretical possibility that doesn't match reality? The answer matters practically for exactly one reason. It determines how you think about everything you do right now. If the universe ends in heat death, nothing you do matters on cosmic scales. Every achievement, every structure, every idea eventually dissolves into uniform thermal equilibrium. Maximum entropy, no gradients, no complexity, nothing. But if the universe ends in a big crunch, something different happens. All matter and energy converge back to a singularity. The conditions that produced the Big Bang get recreated, and nobody knows what happens at that boundary. Does time reverse? Does a new universe begin? Do the laws of physics persist through the transition or get rewritten entirely? The heat-death scenario is philosophically nihilistic. Your existence is a temporary decrease in local entropy that the universe will eventually erase completely. The Big Crunch scenario is philosophically ambiguous. Your existence contributes to a cosmic process whose endpoint we cannot characterize. Those sound like abstract philosophical distinctions. They're not. They determine whether the universe is fundamentally creative or fundamentally dissipative, whether complexity is a temporary accident or part of a larger cycle, whether meaning can persist beyond individual lifespans or gets erased by thermodynamics. You might think none of this affects your daily decisions. You'd be wrong. Cultures that believe in cyclical time behave differently from cultures that believe in linear time. Societies that view existence as temporary develop different priorities from societies that view existence as part of an eternal return. Your cosmology shapes your values, whether you realize it or not. And right now, your cosmology is in flux. 20 years ago, the scientific consensus was heat death, eternal expansion, maximum entropy. That consensus shaped how scientists thought about the long-term future, how they prioritized research, what questions seemed worth pursuing. Today, that consensus is fracturing. The Big Crunch is back on the table. Not as speculation, as a testable hypothesis with supporting observational data. And if it's correct, the entire framework for thinking about cosmic futures needs revision. Here's what makes this moment unusual. You're living through a potential paradigm shift in real time. The data is arriving now. The debates are happening now. The next decade will likely determine which scenario is correct. You'll know the answer before you're old. That almost never happens. Most paradigm shifts in physics occur over generations. Relativity took decades to become consensus. Quantum mechanics took longer. The Big Bang model wasn't fully accepted until the cosmic microwave background was discovered in 1965, 30 years after the theory was first proposed. But cosmological observation technology has accelerated dramatically. DESI mapped 47 million galaxies in a few years. The next generation of instruments will map billions. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire visible sky every few nights starting in 2025. The data volume will be unprecedented. Within 10 years, we'll have enough observational data to distinguish between competing models with high statistical confidence. The Big Crunch prediction will either be confirmed or ruled out. You won't have to wait for the next generation of physicists to settle the question. You'll see it resolved yourself. Assuming you're paying attention, which most people aren't, this is arguably the most important scientific question currently under investigation, and public awareness is minimal. Most people still think the universe will expand forever, because that's what the textbooks said 20 years ago. The textbooks are being rewritten right now. So what happens if the Big Crunch is real? Practically nothing changes for billions of years. The expansion continues, stars form, galaxies evolve, life develops wherever conditions permit. The universe looks identical, whether it's heading toward heat death or eventual contraction, until you get close to the turnaround point. That turnaround occurs roughly 11 billion years from now, according to current models. Before that point, expansion gradually slows but never stops. After that point, everything reverses. Galaxies that were moving apart start moving together. The cosmic microwave background temperature, currently 2.7 Kelvin, starts rising. Space contracts, the contraction accelerates. Just as dark energy currently accelerates expansion, a negative cosmological constant accelerates contraction. Galaxies collide more frequently. Stars get disrupted by tidal forces as space itself compresses. Eventually, the density increases enough that thermal radiation becomes intense. The universe heats up. In the final stages, temperatures exceed anything that exists today. Matter breaks down into constituent particles. Atoms can't hold together under those conditions. Eventually, even atomic nuclei disintegrate. Everything converges toward a singularity. What happens at the singularity is unknown. General relativity breaks down at that scale. Quantum effects dominate. The equations produce infinities that nobody knows how to interpret physically. Maybe time stops. Maybe it reverses. Maybe the singularity bounces and produces a new Big Bang. Maybe the laws of physics themselves get reset. We don't know. And we won't know until we develop a theory of quantum gravity that successfully merges general relativity with quantum mechanics at singularity conditions. That theory doesn't exist yet, but here's the part that should genuinely unsettle you. If the Big Crunch happens, then the Big Bang that started our universe might have been the end point of a previous contraction, which means the cycle could be eternal. Crunch, bang, expansion, contraction, crunch, bang, repeating indefinitely through time. Each cycle might have different physical constants, different laws, different particles, different possibilities for complexity. Our universe could be one iteration in an infinite series, each one exploring different configurations of physical law. That's the cyclic cosmology model. It's speculative. It requires physics we don't have yet. But if the Big Crunch is real, cyclic cosmology becomes a serious contender for explaining why our universe has the specific properties it does. We're not a unique creation, we're one iteration in an ongoing process. Does that make you more significant or less? Both. Less significant because you're part of a repeating cycle rather than a unique occurrence. More significant because the cycle itself might require conscious observers to close some quantum mechanical loop we don't understand yet. Consciousness might be necessary for the universe to complete its cycle and begin again. Pure speculation. But the Big Crunch makes that speculation worth taking seriously in a way heat death never did. Now consider the alternative research from Radboud University about extended Hawking radiation. They calculated that matter itself evaporates on timescales of 10 to the 78th years, much faster than the previous estimate of 10 to the 100th years, but still incomprehensibly long. If they're right, then even if the Big Crunch doesn't happen, matter doesn't last forever. Everything eventually radiates away. Neutron stars evaporate. White dwarfs evaporate. Even planets and asteroids slowly leak particles through quantum processes until nothing remains but diffuse radiation in an expanding void. That's still a form of heat death. But it's faster than we thought. And it means the universe has a definitive endpoint for material existence, even in the eternal expansion scenario. The timescale is so long, it's effectively meaningless for anything biological, but it's finite. So both scenarios, Big Crunch and heat death, end in some form of termination. The question is which type? Collapse or evaporation? Singularity or void? Your life occurs in the narrow window where neither has begun, where complexity is possible, where stars shine and planets orbit, and molecules assemble into patterns capable of contemplating their own existence. That window is temporary in both scenarios. What you do with that window is the only question that matters cosmologically. The universe gave you a brief opportunity to be complex, conscious, and capable of understanding where you came from. What happens next depends entirely on whether you use that opportunity to create something that outlasts your individual existence, or waste it on concerns that won't matter a century from now. The big crunch, if it's real, happens in 20 billion years. You have maybe 80 years if you're lucky. That's the scale mismatch you're working with. Cosmological time versus human time. But human time is where everything meaningful happens, where decisions get made, where knowledge accumulates, where civilizations either solve their problems or fail to. The universe doesn't care which. You should. Because if the big crunch teaches us anything, it's that everything ends. Expansion ends, contraction ends. Each cycle, if cycles exist, ends. What persists is the pattern, the information, the structure that gets encoded in whatever survives the transition. You're part of that pattern right now. What you encode in your brief window of complexity might be the only thing about this era that matters to whatever comes after the crunch. Make it count. If this is correct, nothing changes for you tomorrow. The sun rises, you go about your life. The cosmic clock ticks forward imperceptibly, but something fundamental shifts in how you think about where all this is going. For 2 decades, the operating assumption was expansion without end, an eternal universe growing colder, darker, emptier. That future felt abstract enough to ignore, safe enough to file away as someone else's problem in some incomprehensible distant time. The new data removes that safety. The universe gets an expiration date, not theoretical, calculable. 20 billion years is a long time by any human measure, but it's no longer infinite. It's a number, and numbers have weight. What matters about this discovery isn't the timeline itself. It's what the timeline reveals about the nature of the universe you're living in. You're not observing a static system that will continue unchanged forever. You're inside something dynamic, something that had a beginning, reached a peak, and will end. A life cycle, not an eternal state. That distinction matters philosophically in ways that extend beyond cosmology. If the universe is finite, then everything within it operates under different constraints than if the universe were infinite. Your existence isn't a random occurrence in an endless expanse. It's a specific moment in a specific phase of a process with defined boundaries. The midpoint matters too. We exist when the universe is at maximum expansion, maximum complexity, maximum capacity for structures like galaxies and stars and planets and consciousness. That's not coincidence, that's correlation. Complexity requires specific conditions. Those conditions exist now because of where we are in the cosmic life cycle. Earlier would be too hot, too dense. Later would be too dispersed, too cold. Now is the window. And consciousness emerged during that window, precisely because the window exists. You can't have observers without complexity. You can't have complexity without the right cosmic conditions. The conditions exist temporarily, so observers exist temporarily. What you do during that temporary window becomes the only thing that persists beyond your individual existence. Knowledge, patterns, information encoded in forms durable enough to survive whatever comes next. That's what matters. The big crunch, if it happens, resets the physical state. But information can survive phase transitions. It survives in mathematics, in patterns that reassert themselves under similar conditions, in structures that emerge whenever the underlying physics permits. You're one of those structures right now. What patterns you encode, what information you preserve, determines whether anything about this era matters to whatever follows. Not in some mystical sense, in a straightforward physical sense. Information that persists has influence. Information that dissipates doesn't. The Radboud research on matter evaporation tells you that even in the heat-death scenario, nothing physical lasts forever. The heat-death timeline is longer, But the end point is the same. Everything material eventually disappears. What survives in any scenario is pattern, structure, the mathematical relationships that describe how things work. Those persist because they're not physical objects. They're descriptions of how physical objects behave under specific conditions, and descriptions survive when the objects themselves don't. This is why science matters. Why understanding matters. Why encoding what you learn in forms that outlast your individual existence matters. You're not just living through time. You're participating in a process that spans the entire life cycle of the universe. The data will continue arriving. DESI keeps observing. New instruments come online. Within a decade, the statistical significance crosses the threshold from compelling to conclusive. You'll know whether the big crunch is real or whether we're heading toward heat death after all. Either way, the answer reveals something profound about the nature of time, existence, and what it means to be conscious during the brief window when consciousness is possible. You're not watching this from outside. You're inside it, part of the system. Your choices contribute to what the universe becomes in its remaining time. 20 billion years sounds like forever. It's not. It's the third act of a story that began 13.8 billion years ago. You exist during the critical middle section, the part where complexity peaks, where possibilities maximize, where what happens next depends on what conscious systems choose to do with the resources and time available. The universe doesn't care what you choose. It will contract or expand according to physics, regardless of what any observer does or thinks. But what information persists, what patterns survive, what understanding carries forward, those depend entirely on what you do right now. The clock is running, the data is arriving, the answer is emerging, and you're here to see it happen in real time, which makes you one of the first conscious observers in cosmic history capable of knowing how the story ends. That knowledge is either paralyzing or liberating, depending on what you do with it. If you treat it as permission to give up, because nothing matters on cosmic scales, you've missed the point entirely. If you treat it as motivation to encode something worth preserving before the window closes, you've understood exactly what this discovery means. The universe gave you complexity, consciousness, and time. Limited time, but real time. What you build with it determines whether your existence was signal or noise in the cosmic pattern. Choose signal.